Okay, still talking about work energy theorem here, and remember that friction can do work as well. And even though the force of friction doesn't produce motion, it does change the motion, because we can draw a free body diagram like this, and if we can imagine that this object is moving in this direction, force of friction will be pulling against it. This force of friction is slowing the object down, and it is parallel to the direction of motion. So remember that work equals force times distance. That frictional force is applied over a certain distance, and therefore it is going to do a certain amount of work. So let's read this first problem. We have a 50 kilogram skier hits a flat slope and coasts for 20 meters. So hits a slope, and you're going to slow down and eventually come to a stop after 20 meters. Want to know how much work was done by friction. Okay, and they give us mu, which is the coefficient of friction. Once again, I'm still going to start with this work energy theorem. Work equals delta E equals FD. What are we looking for? Well, we're looking for work. I mean, I'm not, because I have a job, but maybe you are. That was a joke. You can laugh. Looking for work. Work done by friction. So don't let this confuse you. What work was done by friction? How much work? This word right here is what you need to key in on. How much work was done by friction? So the next question again is, do we use delta E or do we use FD? Well, we don't have a force. We don't have the force of friction. Friction is what's causing this person to slow down. Don't have the force of friction. But we do have a distance. So how can we find the force of friction? Well, they give you the coefficient of friction. And if they give you the coefficient of friction, that's going to be a dead giveaway that you're probably going to be using this friction equation, which is the only place that we find mu, the coefficient of friction. So we can solve for this force of friction, and then we can plug it in here for this force. Question is, what's the normal force? Well, remember that the normal force, so if this is the force of the weight, the normal force is the force that's pushing up by a surface to counteract the force of gravity, or the weight. So the normal force in all of these cases is going to be equal to the force of gravity, or the weight. Right? And the force of gravity, the weight, remember, we find by using this equation, weight equals mass times gravity. So I can take this and plug it in here, and I'll calculate the force of friction first. So force of friction equals mu, which is 0.1, times the normal force, which is mass times gravity. Mass is 50, and gravity is 9.8. And if you calculate that out, you get a force of friction of 49 newtons. That's the force of friction. That's the force that's doing the work. Remember, we want to find the work in this problem. So it's kind of a two-step problem. We've got to find the force first, and we'll take this force and plug it in here for force of friction. So work equals force times distance, and the force is 49 newtons, and the distance they give us was 20 meters. And 49 times 20 will give you a work of 980 joules. That is your final answer on this problem. That's the work that's done by friction. Which, by the way, if it takes 980 joules of work to slow this skier down to a stop, another good question would be, how much energy did he have before he started to stop? The answer would be 980 joules, because of the work energy theorem. Work equals change in energy. If there was 980 joules of work done, that means that there had to have been 980 joules of energy lost in that friction slowing down episode. Alright, let's look at this next problem. This one's just a bit more complicated, a few more things to do. But we're going to start the same way and think about it the same way. You're in your new car, The car has a mass of 957 kilograms. You're moving at 30 meters per second. You see a red light and you slam on your brakes. All right, takes you 125 meters before you actually come to a stop. And you want to determine, first of all, the frictional force of the brakes, and then we want to know the coefficient of friction of the brake pads. And don't forget, coefficient of friction is mu. So again, we'll start with the work energy theorem. Part A, what are we looking for? Looking for the frictional force of the brakes. Well, that's this. Okay. Now, in the previous problem, to find the frictional force, we were using this friction equation. But the only reason we did that is because they gave us the coefficient of friction. They don't give us coefficient of friction here. So we cannot use the friction equation to solve for this frictional force to find it directly. What we're going to have to do is we're going to have to use the work energy theorem itself to solve for the frictional force. Okay, so we want to find the force, and they give us a distance. They definitely give us a distance. So this is going to be part of the equation for sure. And now the question is, do we use delta E or do we use work? Well, we know that we were moving at 30 meters per second, and we know that we eventually stopped. So we can calculate the change in kinetic energy. So this can be delta E. And delta E is final energy minus initial energy. And the final energy, we know we came to a stop, so the final energy is definitely going to be 0. There's no potential energy, there's no kinetic energy then. The initial energy, we were moving at 30 meters per second. It's kinetic energy, so that's 1/2 mv/bi, the initial velocity, because the final velocity was 0. 1/2 mv squared is kinetic energy, equals Fd. And now we just plug in and solve for the force. So 1/2, mass is 957, initial velocity is 30 squared, need the force, that's what we're solving for, and the distance is 125 meters. This kinetic energy comes out to be 430,650. Divide both sides by 125, and you get a force, a frictional force in this case, of negative 3445.2 newtons, but you can leave out the 0.2. Negative 3445 is fine. We'll just make that positive. Okay, because with force and energy, we're not really concerned about negatives, at least in this class, for our purposes. Alright, but we're not finished yet. This was part A. We found the frictional force, so that's A. We're done with A. Now we need to find the coefficient of friction. Well, once again, the only place that you can go to for the coefficient of friction is the friction formula. We just found the friction force. That'll go in here. And the normal force, don't forget, equals the weight, which is mass times gravity. So we can change this to be mu times mass times gravity and substitute our numbers in. 3445. Remember, we want to make this positive. We don't want a negative in here for our friction equation. Mu is what we want to know. Mass is 957 and gravity is 9.8. This will give us the normal force. We don't have to directly calculate it. We can plug it directly into the calculator and do it that way. If you calculate that out, the next step would be mu times 9378.6. Divide both sides by 9378.6. And you will come out with a coefficient of friction of 0.37. And don't forget that the coefficient of friction is unitless. So that is our answer to B. Notice you need to check yourself every time you're solving for the coefficient of friction, because it's got to be between 0 and 1. If you get a number greater than 1, you've done something wrong.